Okay, so this is the outline of chapter 21, the Coulomb's law. In Chinese, it is called Coulomb 定律. And next part we'll talk about the charge is quantized and charge is conserved. So actually chapter 21 is really, really easy, even easy for high school students. Actually, maybe in high school, you should have learned some about the electromagnetism. Yeah, but you should not have learned the multivariable calculus before, so it will not go into very deep. Usually in high school physics, it will assume something will be like constant, so that you don't need to deal with the multivariable calculus. Yeah, the double integral, triple integral, line integral, surface integral, so on and so forth. So to let you calculate something based on some physics knowledge, but it might be harder than using calculus because now we will try to use calculus to solve some problem that you may not be able to solve without the calculus. But yeah, so the difficulty goes to the calculus itself, and and the calculus itself explain why it looks like that. So the difficulty will look like, the mathematics is very difficult. I will just try to explain all, if not all, most of the equation. How do we derive of them? Yeah, if you can accept it, then it's fine. If you cannot accept it, then you can just maybe remember it is correct. And actually in the quiz and also midterm final exam, I will just give you some formula paper, just summarize most of the highlight equation so that you don't need to remember too much. Okay, so this is the outline, and so at the beginning, there is a question. It asks, is it a magic? So here you can see, so this is a ceiling with a line hanging a glass rod. So the two glass rods were each rubbed with a steel cloth, and one was suspended by thread, which means that we have a glass rod here, and then hang it with a line, and then we have another glass rod here. You use a steel cloth to rub these two glass rods, and then you'll find that if you just place this one close to the one hanging, then they will repel each other, which means they push each other away. So you don't necessarily need to remember the steel cloth, why it is glass. Don't need to remember that. It's just an introduction. So here we'll find that if they repel each other, which means that there are some forces pushing this one to the top left and pushing this one to the bottom right, based on the mechanics you learn in the physics 1 or in high school. Okay, so now the point here is repel. Why do they repel? And there is another experiment. Still, we have a glass rod hanging here, and then we change a glass rod into a plastic one. And now we use a fur to rub this plastic rod. So the phenomenon are totally opposite with the top one, which is like these two rods will attract each other. They will attract each other, which means a force pushing them together. So what makes these two experiments different? So it is a magic, or it is physics. So now we try to explain this using some assumption, or maybe physics assumption. So using this, we use maybe there are some charge on the glass. So there are some positive charge after rubbing the glass rod with the skew rod, skew cloth, and there are some positive charge remain on both of the glass rod. So in primary school, you should have learned that positive and positive will repel each other, or with the same polarity of the charge, they will repel each other, and with opposite polarity of charge, they will attract each other. So if we have glass rod using steel rod to rub them, so they will also have a positive charge on them, so they will repel each other. But when we change the glass rod into a plastic one, then after we use a fur to rub it, then there will be negative charge on it. So it is they are positive, they are opposite charge, then they will attract each other. So we try to explain this two experiment by introducing the polarity of charge. So the plus sign indicate positive net charge, and the minus sign indicate a negative net charge. So particle with the same sign of electrical charge repel each other, and particle with opposite sign attract each other. So you should have learned it in primary school, easy. Okay, so now we also introduce some materials which are classified based on their ability to move charge. So there are 4 types of material here. Of course, if you really need to distinguish it, then maybe there are even more. But generally, we will classify the material based on the conductivity, into 4 types. So the first one is conductor, doughty, a material in which a significant number of electrons are free to move. Example include metals. So which means when you learn the chemistry, you should have learned the periodic table. So in the periodic table on the left-hand side, just say the 1A, 2A, 3A, and probably they are metals. Of course, the conductivity are different, but generally they will call metal or conductors. So for the conductors, you know, there are some free electrons, 自由电子, free to move, 自由的移动. So there are some free electrons to move, because when you learn chemistry, for the 1A, just say Na. Just say Na. There will be 1 electron in the outer orbit. So that will be the free electron. So the atomic number for the Na is 9, which means that Na is 9. Yeah, 9. Oh, 10. Oh, just forget it. My chemistry is not very good. So yeah, there will be some free electron at the outer orbit. So they are actually the free electrons. And for the free electrons, they are free to move from a, so just say this is a metal and there are many atoms, and there are some electrons free to move from here to there. So and and the movement for the electron is actually the current. So as much as there are plenty of electrons, then the conductivity of the metal will be good. And on the other hand, there will be something called the insulator, 绝缘体, which are generally on the right-hand side of the periodic table. So there are not the charged particle in the non-conductor are not free to move. Example include rubber, plastic, glass. So all of these are organic material. So they have a large molecule. So they don't have, which means that they have a covalence bond, something like I don't really remember what is the chemical formula for this material, but just say for the organic material is something like CH4 +1. So it is like CH. So these are the covalence bond, 共价键 covalence bond. So all the electrons are bounded here. They are not free to move, so they don't have a conductivity. And for example, for the O2, they have a double covalence bond, so still something like 1, 2, 3, 4, something like that. Yeah. So generally for the element on the right hand side of the periodic table, they don't have free electrons, so the conductivity is low. And the third type is called the semiconductor, which is mainly lie in the middle part of the periodic table. The most famous one is of course the silicon. In Chinese we call it Gui. In Taiwan we call it Xi. So the most famous semiconductor is the silicon, because when we use our mobile phone or any other electronic device, most of the chip are formed with the silicon. And of course, for our lab, we are VLSI lab. We are designing chips based on the silicon. And of course, there are some other material called germanium or whatever. There are some other process for the chips for other purpose, maybe for high power purpose, and they will use some other material. But for the silicon, actually the material is cheap because you can find the sand throughout the earth. And actually, the semiconductor has are material that are intermediate between conductors and insulators, which means that it has some free electrons, less than conductors but more than insulator. Why do we need to use it? Why don't we just use conductor? Because conductor, it has less resistance, then there will be less loss. But for the semiconductor, it has some nonlinearity properties. Probably you will also learn the applied electronics this semester, probably. I'm not really sure. And in that course, you will start to learn something like the PN junction, BJT, MOSFET, something like that. And which means that we can you can control the resistance of those kinds of a device. So it will be useful for us to design something like the logic circuit, amplifier, something like that. For the conductor, the resistance is fixed as much as the shape of the wire cannot change suddenly. So you can barely not varies the resistance of a wire, given a specific material and also the length or the cross section area. Then the resistance will be more or less fixed. So semiconductor will be more useful. And another one is called the superconductor. Superconductor are some fancy stuff. You will probably not learn it in bachelor's class, but I just mentioned it here. So superconductor are something like material that have a perfect conductance. It's a perfect conductor, but based on a very strict condition, which is something like near 0 Kelvin, 绝对零度，接近绝对零度 near 0 Kelvin, which means it is a very, very, very low temperature, because as you know, the absolute 0 Kelvin is like minus 220 minus 273 degrees Celsius. This is 0 K. Of course, we cannot really achieve 0 K. Maybe we can achieve 1 K or lower than 1 K or 3 or 4 K. Then, yeah, actually at that time they find the liquid helium, then the liquid helium and can achieve something like 4 Kelvin. 4 Kelvin. So for the 4 Kelvin, which is like minus 269 degrees Celsius. So maybe we can manipulate the pressure, the air pressure, then it can achieve even lower temperature. And at that time, when the physician or the chemistry find the liquid helium, then they can just cooling down the circuit, and then they find the superconductor phenomenon. Yeah, it's just fancy. If the temperature goes to really, really low, then the conductor will, or maybe some of the material will turn into superconductor, and it has nearly low conductance, nearly low resistance. Yeah, it's fancy stuff. Okay, so let's go back here. So here, it mentioned that charged particles, the property of conductor and inductor are due to structure and electrical nature of atoms. And okay, so atoms consist of positive charge, we call it protons, and negative charge electrons, and also neutrons, which is electrically neutral. So in high school chemistry, you should have learned the proton, 质子 中子 中子是 neutron, 电子是 electrons. So you should have learned of them. So proton and neutron have nearly the same mass, but proton has a positive positive E charge, and for the electron, it nearly have no mass. Maybe it is like 9.11 times 10 to minus 31 kilogram. Yeah, but is much lighter than the proton and neutron. And it has negative E charges. And for the neutrons, it is electrically neutral, no charge on the neutrons. So the proton and neutrons are packed tight together in the central nucleus and do not move. So in high school chemistry, you know that for an atom, there will be nucleus. It consists of P and N, certain number of P and N. Given the number of proton, then you know what is the element of it, and maybe there are different number of neutrons. So it is the isotope of the element. And for an atom, there will be same number of electron and proton, so that within an atom there will be electrically neutral, and the electron there will be some orbits, maybe spherical or maybe other shape. So this is what you have learned in high school chemistry. What is an atom? It consists of a proton, neutron, and electron. So yeah, so when atoms of a conductor like copper comes together form a solid, some of them are most loosely held, which means the electron on the outer orbit are so-called the free electron. They are free to move. Yeah, if some of the electrons just leave the atom, then the atom itself will be positive charge because it loses some of the negative charge. And originally it is electrically neutral. If it loses some of the negative electrons, negative charge, then it itself will become positive charge. We'll call it positive ions. We call the mobile electron the conduction electrons, 导电的电子, or free electrons. There are few, if any, free electron in non-conductors. Yeah. So for the previous experiment, we just rub the plastic wad with the fur so that it forms some induced charge. Not that way. It has some excess charge, but induced charge is another stuff. So this is another experiment. Now we have the plastic rod with the fur, so it has negative charge. And this one is originally a neutral copper, which has no charge on it at all. So now if we place this charged plastic close to this copper rod, which is neutral copper rod, then it will induce some charge in this side. There will be some positive charge at this side and negative charge at the other side. And in that case, this is negative charge, this is positive charge. They will attract each other. So the phenomenon is like here, the conduction electron in the copper rod are repelled to the far end, that wad of the rod, by the negative charge of the plastic rod. Because the electrons are free to move, the nucleus cannot move. So as much as we place this rod close to this copper rod, the electrons are repelled by this plastic rod, so they go to the other side. So the E will go to the other side. And the nuclei are not free to move, so that is still there. So in this side, it will be positive charge. At this side, there will be negative charge. So there are so-called induced charge. Yeah. Yeah. Okay. Okay, so next we talk about the charge. The charge. So this definition is a little bit strange. Usually when we try to define something, we will say, this thing is equal to something else. But here is not the same case. It's now we will try to tell what is charge, but here we have current here. So the current here is the derivative of the charge with respect to time. So actually you have learned the calculus. According to the fundamental theorem of the calculus, you will know Q is actually the integration of the I from something to something else, from some time to another time. But yeah, as a definition, it may not be a good one. So here is still mentioned that actually the charge, the current, is a time derivative of the charge, time derivative of the charge. So we will write it as I equals dq dt. We may use it in the later semester, although it's just like a definition. You may not use it, but actually we will actually use it later on. So for the physics class, one thing is very important is the SI unit. SI unit is a very, 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 very important point. So in the quiz, in the exam, when there are some answer with SI unit, if you don't write it correctly, everyone counts for 1 point. It might not be too much, but but everyone will count for 1 point. So be careful about the SI unit. Maybe you need to memorize it a bit. But for easy user student, I think you really need to memorize it. I think you need to memorize it. Maybe you feel there are a lot, but actually it isn't necessary a lot, because maybe for charge you have Coulomb before. For current you have ampere. Just say Coulomb is the SI unit for the charge. Is the SI unit of the charge. So we will write it as C or with a prefix Yeah, and So here for the current, you know, the SI unit is ampere. So based on this one, you can just simply write. So I has a SI unit of C. And then for this dq dt is something like the charge is divided by the time. So for the time, you must have known it. The SI unit for the time is second, and the SI unit for the charge is this is A. Ampere for the current, Coulomb for the charge. So we can simply find that A is actually Coulomb per second. Or here we can write it as C equals A times S. So this is the conversion of the SI unit. Yeah. So you don't really need to memory a lot. You just need to memorize something and use some simple equation, and then you just plug in the SI unit, and then you can find the relationship between different SI units. Okay, so here we come to the most important part in this chapter, which is still very easy, I think. So here we talk about the Coulomb's law. So the Coulomb's law describes the electrostatic force. Electrostatic force. 静电力啊，静电力。Between two charged particles between two charged particles. So if the particle have charge Q1 and Q2 are separated by distance R and are at rest, why we call it static? It is just an assumption. Actually, I think in the practical world, it is nearly impossible to find it naturally. Something is totally at rest, totally at rest. Even though you feel like you are just sitting on your seat, but actually the atom inside you is something like oscillating. They cannot really at rest totally. So it's just an assumption. So assume the two charge Q1, Q2 are at rest or moving slowly relative to each other. Then the magnitude of the force acting on each due to other is given by this equation. So I think you should have learned it in high school. Yeah, and here we have the epsilon naught 8.85 times 10 to the minus 12 Coulomb square and m square. So you don't really need to remember this one. I will generally provide some constant during the quiz and exam. Yeah, so this is epsilon naught is so-called the permittivity constant. Permittivity constant 导电率，导电常数。Permittivity constant. When you learn the electrostatics in chapter 28, you will also learn mu naught, which is called the permeability constant. 磁导常数 And usually this 1 over 4 pi epsilon naught will appear in together. This fixed term will generally appear together. Sometimes you will see epsilon naught appear independently, but generally 1 over 4 pi epsilon naught will appear together. So this ratio, we usually will simplify it as K. K is the whole term, 1 over 4 pi epsilon naught. So which is 8.99 times 10 to the 9, the SI unit, like this. Okay. So for this equation, we already know what is this one. So you know this is the force, this is the charge, and this is the distance between them. So you can see here, this is a graph. So as much as we have Q1, we have Q1 here, Q2 here. So we use a line. We use a line to connect them together. So this R hat is the unit vector. This is the unit vector. Unit vector means the magnitude of it is 1. The magnitude of a unit vector is always 1. At least in some fundamental course, if you learn something like the tensor algebra, the length of a unit vector is not necessarily 1, but yeah, just forget it now. But yeah, so generally when we have a unit vector here, then the magnitude of it is 1. So how do we consider the R hat? So for this one, from Q2 to Q1, we will consider the force F here. So the R axis is pointing to that side. This is the R axis. And in that case, R hat point to the same position. R hat point to the same position, which means for Q1, R hat point to the right side. And when we consider the force acting on Q2, the R axis is the other way around. So when we consider this way, this is the R axis. This is the F acting on Q2. And in that case, R hat pointing to the left side. R hat pointing to the left side. So suppose Q1 and Q2 are both positive charge. So this term is positive. This constant is also positive. R squared is of course positive. So which means that this whole term is positive, which means that the force has the same direction as the R hat. So in that case, this is positive, this is positive. R hat is like this direction, so F points to the right side for Q1, and F points to the left side. This is R hat, this is F. So which means that the force acting on Q2 points to the left, force acting on Q1 is pointed to the right. So they repel each other. And there are some other cases if both of the charge are negative charge, which means that Q1 is negative, Q2 is negative, but negative times negative is positive. So this term is still positive. This is positive, this is positive. This whole term is positive, which means that the F has the same direction as the R hat. So in this case, the F still have the same direction. The F still have the same direction as the R hat. R hat like this. This is R hat for this charge. So they still repelling each other. They're still repelling each other. And there is another case, positive, negative. Maybe you will feel that there is still negative, positive, but actually they are the same. So we just mentioned one of the charges is positive and another one is negative. So here, just say Q1 is positive, Q2 is negative. So this term is negative. Q1 and Q2 is negative. Q1, Q2 is negative. So this is negative, this is positive, this is positive. So in this case, the whole term is negative, which means the F has an opposite direction with the R hat. So here, still R hat points to this side, R hat points to the other side. And so F has the opposite direction as the R hat. So F points to this side for this charge. And then F points to the right side for the positive charge. So which means that these two charges will attract each other. So the punchline for this equation is that no matter whether the charges are positive or negative, you just plug in it here, and then you just follow the definition of the R hat, then you know it already tells you that whether the force is attracting the charge or repelling the charge. So this is the punchline of this equation. So two charged particles repel each other if they have a same sign of charge, either both positive or both negative. They attract each other if they have opposite sign of charge. But for the Coulomb's law, it is more than what you have learned in primary school. For the primary school, you only know that same sign of charge repel and opposite sign attract. And here, Coulomb's law also tells you that how large is the force attracting or repelling the charged particle. So it is proportional to the charges, to the product of the charges, and inverse proportional to the square of the distance. Which means that if the charges are farther away from each other, then the force will be weaker. And if the charge is larger, then the force will be stronger. And just now we only mentioned about the electrostatic the electrostatic force between two charged particles. If there are more than two charged particles, then we need to calculate it one by one, and then we add them together with the vector sum. So if we write it in a formula, it is like if we have n charges. So the force acting on the charge 1 will be like the Coulomb force from the charge 2, which is F12, the charge 2 acting on charge 1, which is F12, and then adding F13, so on and so forth up to F1n. So suppose we have n charged particle, there will be n minus 1 force acting on F1, and so as the other, although we don't write it out one by one. Just say if we have a charge here, if we have a charge, this is Q1, maybe a positive charge, and then Q2 is a negative charge, Q3 is a positive charge. So when we consider the force acting on Q1, so we'll know that Q2 and Q1 are opposite signs, so they attract each other. And for Q1 and Q3, they will repel each other. And of course, they will attract each other. So when we consider Q1, the total force will be something like this. So this is the total force F1 net will be like that. Q2 F2 net will be something like that. Q3 F3 net will be something like that. So it just follow the vector sum, not the scalar sum. Scalar sum is just like 1 plus 1 is 2, 1 plus 2 is 3, something like that. But for vector sum, if we have two vector which are perpendicular to each other, both of them has a magnitude of 1, then the sum of them will be something like square root of 2. Something like that. This is the vector sum. I think you should have learned it in high school. So this is the case when we consider multiple electrostatic forces for multiple charges. So we just need to calculate one by one and add them together with the vector sum. So next we will introduce the cell theories. I will not try to explain why it will like this, because we will try to explain it later when in chapter 23. When we talk about the Gauss law, we will have some strong evidence to explain why it will be look like this. But now you can just accept it. It is something called the theory or the theorem. So for the cell theories, there are two cases. The first one is like a charged particle outside a shell with charge uniformly distributed on its surface is attracted or repelled as if the shell charge were concentrated as a particle at its center. So maybe I can draw a figure. Let me see. So it mentioned that for shell theory 1, it is like, so it mentioned that if you have a sphere is 球体啦，它不是平面的。It's a 3D sphere, and assume the charge on it are uniform on the surface. The total charge may be Q, And then you consider another charge. Maybe this is Q1, this is Q2. And the distance between this point to here is R. So maybe you'll find it's difficult because the charge are uniformly distribute on the surface. So you may not, if you feel confused, whether we can just assume it. There's another case. If all the Q1 charge are concentrated at the center of this sphere, which means that these two are totally independent. So if we have Q1 charge here, Q2 charge here, they are still separated by R. So here we can simply know that the force acting on them are nothing but the Coulomb's law, 1 over 4 pi epsilon naught Q1 Q2 over R squared, R hat, something like that. But for this case, for the cell theorem, it tells you that this one, you can just regard all the charge are concentrated at the center. So when we talk about the force acting on this one, it is still this case due to the shell theory. Shell theory 1. Yeah. So when you go back to check it again, so a charged particle outside a shell with a charge uniformly distributed is very important on the surface. Is attract or repel as if the shell charge were concentrated as a particle at the center. Actually, if you really need to prove it, using integration, it will be very difficult because you can simply consider maybe for this part. So the distance is R1. This is dQ1. So Q1 is equally uniformly distributed on the sphere. So for this part only, you have only a small amount of charge called dQ1. And then this is the distance. It's not actually R because R is from this point to the center. But for on the surface, not all the point has a distance equal to R. Maybe a small difference, but actually not the same. So for this point is dQ1. Maybe for another point here, this is R2. This is dQ2. So we need to separate all the charge into infinite many small charge, and then we need to use the integration 1 over 4 pi epsilon naught Q2 is the constant, which is a good news, and then over R square dR, something like that. Actually, this is not totally correct from a mathematical point of view. But actually, it would be something like that because we cannot consider it is a charge. If we need to use some very rigorous mathematical proof, then we cannot consider all of them are R. But yeah, the shell theory tells you that it is actually the same. But actually here it tells you that for multiple charge, we need to separate one by one and then we add them together. But for continuous one, when you just separate them into infinite many and then you need to add them together, it is actually a integration or even a double integration because it is a spherical and then we need to go through the spherical, which is a 2D shape. And yeah, so the charge is uniformly distributed on its surface, is attracted or repelled as if the shell charge were concentrated as a particle at the center. Concentrate as a particle at its center. So this is what shell theory 1 tells you. And for shell theory 2, a charged particle inside a shell with charge uniformly distributed on its surface has no net force acting on it due to the shell. Okay, so for the shell theory 2's for the shell theory 2, it tells you that suppose we have also a sphere with charge on the surface. Actually, it's a spherical, so it's just like a moon. So we still have this line, but I just draw it on the outer circle. So suppose there are some charge uniformly distributed on the surface of a sphere. Actually, this is a sphere. Then if we just put a charge Q, whether it is positive or negative, then it tells you that the force acting on this charge will be zero, no matter where is the charge. As much as this charge is inside the spherical, the net force will be zero. For this one, it tells you that this is actually the same case, but if the charge is outside the sphere, then it looks like all the charge are concentrated at the center. But for this case, no matter where is the charge, then the total force will be zero, will all be cancelled. So you can simply imagine like, suppose we just cut it like this. So for this part, it will generate a force pointing to this side. And you can all the way find a symmetric point. For this point, the symmetric point is here. For this point, the symmetric point is here. Then this point will generate the force like this direction. So just say this is x-axis, this is y-axis. So the x-axis component will be cancelled because these 2 points are totally symmetric. And the remaining, so the total force will point to the negative y-axis. So for this part, it will generate force pointing to the bottom. And for this part, it will generate force pointing to the top. You feel like this part is shorter, this part is longer. But also, this part is shorter, but this part is closer to the charge. So this part will generate stronger force for the same segment. This force will be stronger than the force. These 2 segments will generate a force stronger than these 2 segments, but this part is longer. So it turns out that this force generated by this part pointing to the upward, and this part will generate a force pointing to the downward will perfectly cancel. So this is the shell theory 2. So there will be no net force acting on the charge inside a sphere particle with uniform charge distributed on the surface. So this is the shell theory 2. Yeah, so this is a simple explanation for it. Maybe you will not accept it at all, but so far we will not go deep in the integration. But in chapter 23, after we talk about the Gauss law, we can explain it more clearly. But actually, the the difficulty drive on the understanding of the Gauss law, because Gauss law is actually a double integral. Okay, so here the figure shows two protons. So this one is proton, this one is proton, this one is electron on the axis. On the central proton, what is the direction? The force due to the electron. The force, the central proton, the force due to the electron. So this is easy. This is electron, this is proton. They are with opposite sign so that they attract each other. They attract each other, which means that on the central portions, the force due to the electrons point to the left. Maybe I use blue color. So point to the left, and the force due to the other proton. So here, the proton, they have same polarity of charge, so they repel each other, which means that this is also left, and the net force when we add them together, of course, point to the left. So it is easy. Okay, so let's see a sample problem. So for part A, figure A shows two positively charged particles fixed in the place on an x-axis. On the x-axis, the charge are Q1, which is 1.6 times 10 to minus 19 Coulomb. So this number is will appear again and again. So this is called the elementary charge. We will introduce it later. But yeah, so this is Q1, and Q2 is 3.2 times 10 to the minus 19 Coulomb, which is 2 times to this. So, and the particle separation is R, capital R is 0.02 meter. So what are the magnitude and the direction of the electrostatic force, particle 1 from particle 2? So F12 is 1 over 4 pi epsilon naught Q1 Q2 over R squared. So we don't use the vector notation here. We just skip through all the vector notation. We only consider the magnitude here. We just determine the direction of the force by our understanding. Yeah, by our understanding. Actually, you can all the way follow the vector notation, and then you calculate by that kind of calculation. It is also good, but yeah, it's up to you. You can choose either of them, or maybe in the exam or quiz you can do both to see whether they match each other. Okay, so 1 over 4 pi epsilon naught is K, which is 8.99 times 10 to the 9th power, and then we just plug in. Q1 is 1.6 times 10 to minus 19 times Q2 is 3.2 times 10 to minus 19. And then R is 0.02 square. So we need to careful about the SI unit. Usually they will give you Q1, Q2 as the Coulomb, or maybe with some prefix. And for K, it is just fine, 8.99. But for the R, the SI unit is always meter. If you are provided by if you are given the distance with a centimeter, you need to convert it back to meter, so that the formula will be correct. Okay, so yeah, so the answer will be 1.15. That's 1.15 times 10 to minus 24 Newton. And if you write it in the vector form, it will be minus 1.15 times 10 to minus 24 Newton using the unit vector of x. So this is the unit vector in x-axis. In y-axis, we will use I, J, and K hat to specify this is for x-axis, this is for y-axis, this is for z-axis. And maybe you can just draw a dot, but some of the textbooks, it will just give dot. Sometimes I may not write the dot, sometimes I will write the dot, but it's fine as much as this is I hat, J hat, and K hat to stand for the unit vectors for x-axis, y-axis, and z-axis respectively. Okay, so this is easy. So next, now we just place particle 3 between Q1 and Q2. The distance here is 3/4 hour. 3/4 of hour. 3/4 of hour. So what is the net electrostatic force on particle 1 due to particle 2 and 3? So we already calculate F12. So now we also need to calculate Q13. So F13, I can just go quickly. K Q1 Q3 over R 3/4R squared. So this is the distance between Q1 and Q3. So similarly, we have 8.99 times 10 to the 9th power times Q1 is still 1.6 times 10 to minus 19. And then Q3 is minus 3.2. So take the absolute value will be 3.2 times 10 to minus 19. And then 3 times 0.02 over 4, or the whole term square. So finally, we will get this one to be 2.05 times 10 to minus 24 Newton. And as much as they are in opposite sign, the charge are in opposite sign, so they attract each other, which means F13 points to the right side. So if we write it in vector form, F13 equals 2.05 times 10 to minus 24 Newton I. Okay. So next, so this is a bit trouble. This one is placed at an angle. Still, the distance is 3/4R. So in this case, F14 is the magnitude of F14 is still the same, which is 2.05 times 10 to minus 24 Newton. But actually, when we write it in vector form, it will be a bit different. It will be something like this is F14. This theta is 60 degree. This is 60 degree. So this one will be F14 cosine 60 degree. This one will be F14 sine of 60 degree. Okay, in this case, F14 will be 2.05 times 10 to minus 24 cosine 60 degree Newton I plus 2.05 times 10 to minus 24 sine of 60 degree J, which is 1.025 times 10 to minus 24 Newton I plus 1.78 times 10 to minus 24 Newton J. Something like this. Yeah. So this is it. And in that case, let's see. Yeah. So in that case, F1 net, let me see, F13. Oh, I forgot to I forgot to calculate the net charge here. So yeah, let me finish this one first. This one will be F12 plus F14. This one is F12 plus F14, which is minus 1.15. This one times 10 to minus 24 plus this term here. So finally, it will be minus 1.25 times 10 to minus 25 Newton I plus 1.78 times 10 to minus 24 Newton J. So this will be the net force acting on charge 1. And yeah, let me go back to here. Here is F1 net. F1 net is F12 plus F13. Yeah, so this is minus 1.15 times 10 to minus 24 Newton I plus 2.05 times 10 to minus 24 Newton J, which is still I here. I. So the answer will be 9 times 10 to minus 24. Oh, 25 Newton I. So this is the net force for Q1 here. Yeah. Actually, you don't really need to worry about, you cannot copy all the things immediately. Actually, I will just upload this one on the Moodle also. And also you can check the video again. So yeah. Yeah, for the second one, here we talk about yeah, we have a sample problem, another sample. Yeah, it says figure A shows two particles fixed in a place. A particle of charge Q1 equals plus AQ at the origin, and a particle of charge Q2 equals minus 2Q at x equals L, which means the distance between them is capital L. At what point can a proton be placed so that it is in equilibrium? Is that equilibrium stable or unstable? Okay, so yeah. So this is a positive charge, this is a negative charge. This is 8Q, this is minus 2Q. So it asks if we like to place a proton placed in between, which means it is a positive charge. It is a positive charge. Can it be stable? Can it be in equilibrium, which means that there will be no force acting on it? Equilibrium, which means that no force acting on it. Okay, 就是平衡状态, 平衡状态, no force acting on it. So yeah, so there will be 3 segments. Of course, the proton should be placed on x-axis. If it is not on the x-axis, then there will be a y-axis component, which is not good enough. So for the x-axis, there are three regions. One is between them, one is on the left, one is on the right. So let's consider one by one. For the region between the Q1 and Q2, so this is positive, this is positive. So the force acting on the proton will point to the right side. And this is positive, this is negative. They should attract each other. So the force also point to the right side. So both of the force acting on the proton point to the right side. So it can never be cancelled. So this one is discarded. Discarded. For the second case, if the charge placed on the left side, these two are positive, so they repel each other. F1 points to the left side, and don't forget that this is AQ, this is minus 2Q, and for Q2, this is positive, this is negative. So these two are attracting each other, which means that F2 points to the right side. So now F1 and F2 points to opposite direction. Whether it's possible that they can perfectly cancel each other, the answer is no, because Q1 has a magnitude larger than Q2. Just ignore the minus sign here. This is 8Q, this is 2Q. So the force should be stronger for this case, for the magnitude. And for the distance, Q1 is closer to the proton than Q2, which means that for the distance and also for the magnitude of the charge, both of them will make F1 larger than F2, so that they can never be cancelled. So for the third case, if the proton placed on the right side, this is 8Q. Sorry. This is 8Q. This is minus 2Q. So positive, F1 points to the right side. And for Q2, negative, positive. So F2 points to the left side. So this magnitude is large, but the distance is also large. So maybe there is some point that F1 and F2 can equal each other. So let's see how do we find this point. So for the force F1, so we have F1 equals F2, or maybe we can just consider the magnitude, because they point to the opposite direction. So we have a K, F1 should be K times Q1, and we don't know the charge of the proton. We just make it QP over. Okay, suppose this one is L, and maybe this one is X, this one is X. So this is X squared, this is X squared. And for F2, the distance between them will be X minus L. So here we have K times Q2 QP over X minus L squared. So now we can find that K and K can be cancelled, QP and QP can be cancelled. And actually, Q1 is 8Q over X squared equals this is actually 2Q over X minus L squared. So Q and Q can also be cancelled. And then 1 and 8 can cancel. So that it becomes 4. So this is just a quadratic equation. If we try to simplify it, it becomes 4x squared minus 8xl plus sorry, it should be 3x squared plus minus xxl plus 4l squared equals 0. So we can have two solutions. One of the solution is x equals 2/3 L and 2L. So do both of them acceptable? The answer is no. The answer is no. We will reject the first one. Because if x is 2/3 L, which means that it is here, x equals 2/3 L, which means it is between Q1 and Q2. But here we are already assume that the proton should be placed on the right-hand side. And here it makes x minus L become a negative number. So this one should be rejected. We only accept that x equals 2L. X equals 2L. And it also asks you that is that equilibrium point stable or unstable? The answer is unstable. The answer is unstable. You can simply imagine that. If this point, just say here, this is Q1, this is Q2, this is 2L, this is the proton. Okay, so this is positive, this is negative, this is positive. If this proton go to the right side, and actually you need to really go to some calculation to really find that it is really unstable. So actually, now we consider F net acting on the proton will be K times HQ. This is Q1 times QP over X. X, or maybe X equals to 2L plus delta X squared, which means that we try to move the proton from 2L to a very, very small distance to the right for us, very small distance, delta X, and minus K times 2Q QP over L plus delta X. Something like this. So if you try to explain it, it will look like KQP, QQP, and then we have 4, and then expanding this one will be 4L squared plus 4L delta X plus delta X squared minus 1 over L squared plus 2L delta X plus delta X squared. And of course, you can just divide by 4, divide it by 4. So it will look like KQQP and then 1 L squared plus L delta X plus delta X squared over 4 minus 1 over L squared plus 2L delta X plus delta X squared. So you will find this one larger than 0. Because this one is very, very small, ignorable, and you will find this one is smaller than that one, but it is in the denominator. So this term will be larger than this term. So it will be positive and false, which means that if the proton here, Q1, Q2, and this is the proton. Originally, this is 2L. If it moves a bit to the right side, then there will be a force pushing it away, which means that it is unstable, Okay, so maybe let's stop here today, and we will continue next week. Yeah. And of course, if you